Hello, welcome to this video. Today we're going to look at this product, which is also known as the Wallace product. And it states that pi over 2 is equal to 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7 and so on to infinity, which can also be a bit more formally represented by the product as n goes from 1 to infinity of 2n over 2n minus 1 times 2n over 2n plus 1. So let's begin. So we will consider the integral in as the integral from 0 to pi over 2 of sine to the nx dx. Now, in a previous video, I found a reduction formula for the integral of sine to the mx times cosine to the nx, and we can just use that here because in our case, the power of cosine is 0. So the formula is as follows: it's negative 1 over n sine to the n minus 1x cosine x. And this, in our case, goes from x goes from 0 to pi over 2. Then it's plus n minus 1 over n times the integral from 0 to pi over 2 of sine to the n minus 2x dx. Now, this is equal to what? Now, if we plug in pi over 2, we'll have cosine pi over 2, which is 0. If we plug in 0, we'll have a power of 0, sine to the n minus 1 of x, which will be either 0 or, well, 1, depending if n is equal to 1 or not. So what we're going to do is say, well, if n is bigger than or equal to 2, we know this power is bigger than or equal to 1, so if we plug in 0, this does indeed turn out to be 0, meaning that we can just cancel this to 0. And now this will be n minus 1 over n times n minus 2. Okay, now let's try to find out what is I2n and I2n plus 1. So, I2n, by a reduction formula, it's 2n minus 1 over 2n times I2n minus 2. But by a reduction formula again, I2n minus 2 is 2n minus 3 over 2n minus 2. So this is 2n minus 1 over 2n times 2n minus 3 over 2n minus 2 times I2n minus 4, and so on. So we basically expand each I, or use a reduction formula on it, and we end up with the final result of 2n minus 1 over 2n times 2n minus 3 over 2n minus 2 times 2n minus 5 over 2n minus 4, and all the way on to, well, at the end we'll turn I2 to I0, and we'll have ourselves times 1 over 2 at the end times I0. But what's I0? It's exactly the integral from 0 to pi over 2 of sine to the power of 0 times x, which is the integral from 0 to pi over 2 of 1, which is pi over 2. Okay, now let's find out similarly what is I2n plus 1. So by our formula, it's 2n over 2n plus 1 times I to n minus 1. And again, by our formula, it's 2n over 2n plus 1 times 2n minus 2 over 2n minus 1. And this is times I to n minus 3, which, if we keep using our reduction formula again and again, we'll end up with 2n over 2n plus 1 times 2n minus 2 over 2n minus 1 times all the way on to, well, at the end we'll turn I3 to I1, and I3, and when n is equal to 3 we'll have 2 over 3, so this is 2 over 3 times I1. But what's I1? It's the integral from 0 to pi over 2 of sine x dx, which is negative cosine x. And this goes from 0 to pi over 2, meaning that this is cosine 0 minus cosine pi over 2, but cosine 0 is 1. Cosine pi over 2 is 0, so this is 1. So times 1. And these are our two formulas. So now let's explore further I to in and in plus 1. So notice, because on the interval from 0 to pi over 2, so if I draw this, sine to the power of something, sine will be positive, and so sine to the power of something will always be positive. Something like this, meaning that if I multiply this by another sign, it'll be smaller. So it'll go something like this. So this area, which is, say, in plus 1, is bigger than this area, which is, say, in, so this is in plus 1, and in, we can say that in, if this, we know this will be in, and this is in plus 1, because we multiplied our graph by another sign in order to get to the next, in order to get to in plus 1, we can see clearly that the blue area is smaller than the black area, and so we know I to n plus 1, just in plus 1, is smaller than in. So now let's use this. Now, let's see. We know 1 is smaller than I to n over I to n plus 1, because we replace n with 2 in here and divide by in plus 1, which we know is positive, so everything is good. But now, if we replace I to n plus 1 with something even smaller than it, say I to n plus 2, we'll end up with I to n over I to n plus 1 being stuck between these two values, and I to n plus 2. But we know what I to n over I to n plus 2 is. If we plug in 2n plus 2 here, we get I to n plus 2 is equal to 2n plus 1 over 2n plus 2 times I to n. And so, we'll end up that this is 2n plus 2 over 2n plus 1. Alright. But now, let's let n tend to infinity. As n goes to infinity, 1 obviously approaches 1. 2n plus 2 over 2n plus 1 approaches 1. And so, because I to n over I to n plus 1 is sandwiched between these two values, we know it also must tend towards 1. Now let's see I2n over I2n plus 1. We know now what tends to 1? I2n over I2n plus 1. But we know this, it's just this over this. So this is going to be pi over 2 times. So we're going to have 2n minus 1 over 2n times 2n minus 3 over 2n minus 2, so on until 1/2 divided by 2n over 2n plus 1 times 2n minus 2 over 2n minus 1, so on until 2 over 3. But now this is pi over 2 times, let's see, so we have 1 over 2 times 3 over 2, and then next here will be 3 over 4s, and here will be the next one here will be 4 over 5, someone over it is 5 over 4, and then times 5 over 6 times 7 over 6, and so on. And so if we divide by this, it'll just be like doing 1 over each of these, and we'll end up with 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7, and so on. We'll have some n bits at the end, but as n goes to infinity, this will just be an infinite product, and we know this will be precisely pi over 2. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.